Welcome back. We have talked about some kind of broad deployment strategies, talked about static versus dynamic deployment and where to position our units, but now we need to talk about just how many ambulances do we have to have on the road? How many ambulances should we have on the road in order to match our supply to our community's demand? Now we will give you a quick warning. There's going to be a lot of math, a lot of formulas here for you. Please do not memorize these, commit all these to memory. These are just resources for you, and so you understand the thought process behind why we choose, let's say, 5 ambulances over 6 ambulances or 4 ambulances. So first thing we need to do, or one of the things we can do, is calculate the probability of receiving a call during a specific hour. So the probability of x, x being the number of calls during that hour, um, we can we can calculate that. The other variable we need is the average number of calls for that hour. So maybe in your system you want to know EMS base 2 from 6 a.m. to 7 a.m. What's the probability of them receiving 1 call, 2 calls, 3 calls? Well, first we need to know the average number of calls for 6 a.m. to 7 a.m. for EMS base 2. Let's give an example of this again. Let's say EMS base 2, 6 a.m. to 7 a.m. We know that the average number of calls for that time period is 3. So we want to know what's the probability of us receiving 4 calls in that time period. And we can plug this into our formula. So what's the probability of receiving 4 calls? Lambda up there in the numerator is our average number of calls from the area that we're analyzing, raised to the power of 4 calls. Are we gonna receive 4 calls? Then we have the exponential of a negative lambda. So if you're just working on your calculator, you just hit the exponential button, all divided in the denominator, the factorial of x of those 4 calls. And if you remember back to high school algebra, factorials, let's say factorial of 4 would be 4 times 3 times 2 times 1. That together is the factorial, denoted by that exclamation point. So if we wanted the factorial of 3, it would be 3 times 2 times 1, and so on and so forth. So if we do that algebra, if we do the math there and divide it through, we have a probability of 0.168, which translates to a 16.8% chance of receiving 4 calls from 6 a.m. to 7 a.m. from that area when our average runs are 3. Now we can run this formula, this calculation over and over and over again, and just switch out the number of calls. So what's the probability of us receiving 0 calls from 6 a.m. to 7 a.m.? Remember, our average number of calls for that time period is 3. So what's the probability of us receiving 0 calls and being able to sleep in a little bit? Well, again, we can plug in those numbers. So we've got lambda, which is 3, raised to the power of x, which is 0. Any number raised to the power of 0 is 1. On the denominator, we've got the factorial of 0. The factorial of 0 is also 1. So pretty simple calculation there. And we end up with a 0.0498 probability of receiving 0 calls, or just a hair under 5% chance of receiving 0 calls for that time period. Now, what are we going to use this for? Well, first, it's just good to have this information and know your probabilities. We can graph this if you'd like, showing trends. It's fun to pull out and try to impress the upper administration or government officials. But so we've got the average number of calls. We've got these historical trends. If you start noticing that you're breaking these historical trends, Well, then that's something to look at. So the average number of calls is 3, and you start receiving just one call in that time period over the course of a couple months. Well, the probability of receiving one call is fairly low. So what's going on? Same thing with 4 calls. So to go back, the probability of receiving 4 calls is just 17%. It's still fair, relatively low. But for receiving 4 calls over and over and over again for a span of months, something is going on, and it kind of sends up a red flag for us to look at. All right, so next we've got some calculations to do for system capacity, and this is going to drive our decisions of how many ambulances should we have on the road, how many ambulances should we have in service, given the demand and given their utilization and some other factors. So we'll still look at that same time period, 6 a.m. to 7 a.m. Then we'll do a couple things. The first one, we will calculate the probability of all of our units in the system being available. We can think of this as receiving 0 calls. It's a little bit different. We'll point out how and why here in a minute. But what's the probability of all of our units all being available during that hour? And then once we've calculated that, we can calculate the probability of the next call, or the probability of a call coming in between 6 a.m. and 7 a.m., having to wait for a unit to become available to respond to that call. So first, we're going to calculate the probability of all of my ambulance units being available during that hour. We've got 3 variables that we need to input. We've got K, which is the number of ambulances in my system. We've got lambda, which is the average number of calls for that hour. We've already defined lambda or played with lambda here in that previous calculation, so we're familiar with that. And then adding a third one, we've got mu, which is the number of calls that can be handled during a specific period of time. And what we do here is how long does it take on average your system, your units, to complete a call start to finish. So we're going to do 60 divided by our average total call time. So here we're going to say that for our system, we've got maybe a little lengthier transport times. Maybe we're in a little bit of a more rural area. So start to finish, en route to in service, we've got a total time of 1.5 hours. So 60 divided by 90 minutes, it's 0.67. What that tells us is the capacity for each unit in our system on average is 0.6 calls per hour. So all we're going to do is plug these in. Again, just some algebra here for you. If you think back to some algebra classes, you may or may not remember this notation right here is just a summation notation. So we're going to be repeating this calculation once, twice, 3 times, 4 times, however many times are needed. And the summation says we're going to do this once, we're going to do this twice, we're going to do this 3 times, and then we're going to add all those together, and that'll be our number for this portion of the calculation. This summation sign comes with a couple definitions, and one of those is n equals k minus 1. So we've got the factorial of n here, we've got raised to the power of n here. So n equals k minus 1, so the upper bound of n is going to be the average, is the number of ambulances in our system minus 1. So we've got, if we have 5 ambulances in our system, we're going to do this summation 4 times, or up to 4, excuse me. So starting at 0 there on the bottom, we've got n equals 0. So we're starting at 0, and then we're ending at k minus 1. So we're actually doing it 5 times. We've got 0, then we're doing it for 1, then we're doing it for 2, 3, and 4. And then after we've done that summation, we can just plug in the rest of that formula there. So let's run with an example real quick. So in our system from 6 a.m. to 7 a.m., I've got a K of 5, so I've got 5 ambulances in my system. I've got a lambda of 3, and that says that the average number of calls for that time period, 6 a.m. to 7 a.m., is 3 calls. Then they've got mu. So we've already defined mu. We said that the average time for a total call is 1.5 hours, so 60 divided by 90 is 0.67, and all we have to do are plug these in, remembering that the summation sign, and we're starting at n equals 0, and we're ending the summation at k minus 1, so we're ending at an n of 4. When we plug all that in, we get a p0, or a probability of all of my calls, or excuse me, not all of my calls, all of my ambulance units being available during that time period at 0.0052, which is 1/2 of 1%. So it's a 0.5% chance that all 5 of my ambulances will be available between the hours of 6 a.m. and 7 a.m. Now you might be having a moment here where you're saying, well, wait a minute. The probability of all the ambulances being available here between 6 a.m. and 7 a.m. with an average number of calls being 3 is 1/2 of 1%, 0.5%. That doesn't really jive what we did earlier when we said the probability of receiving a call between 6 a.m. and 7 a.m. with an average of 3 calls um, is just under 5%. So we've gone from 5% to 0.5%. Why is that? So what this does here just tells us between 6 a.m. and 7 a.m. what's the probability of us receiving 0 calls. This one here is the probability that all of our ambulances are fully available. So this extends earlier than 6 a.m. because remember our average total call time is 1.5 hours. So if I had an ambulance dispatched to a call at 5 a.m., well, come 6 a.m., they are still on that call and they are not available. So this extends out that, that availability time based on how long it takes your system to run a call. That was step 1. So now we have to move on to step 2, which is the probability of a call during that time period having to wait for an ambulance to mark itself in service in order to respond to that call. So what's the probability of all of our units being tied up during a call and the next 911 call coming in and the dispatcher says we're going to have to wait for a unit to come available. This is step 2 because you'll see in our formula we've got P0 right there. We've got the probability of all of my units being available right there as part of the calculation, part of the formula. So we need to do P0 before we do what we're going to call PW, the probability of having to wait. We're going to use the same variables. We've got K, the number of ambulances in our system. We've got lambda, the average number of calls that we're receiving during that time period, and we've got mu, the number of calls that can be handled. So here we've got that 0.67 since we have average total call time of 1.5 hours. This looks a little hairier than you might think. If we're doing this by hand, pay attention to this first part before the P0. If we go back to this, well, there it is. So if you're doing it by hand, you've already done it. We're just transplanting and then multiplying by P0. So let's plug in the numbers for step 2. We are calculating the probability of a call having to wait on a unit to clear up in order to respond. So my K, the number of ambulances, is 5. The average number of calls for that time period, 6 a.m. to 7 a.m., is 3. My mu is 60 over 90 minutes, which is my average total call time, is 0.67. We've already calculated P0 for this, and that's 0.0052. So if we run this formula, we get to a probability of waiting at 0.747, which is just about a 75% chance that a call coming in, the next call coming in between 6 a.m. and 7 a.m., will have to wait for a unit. And I don't know about you, but if I were that caller, I don't want to see a probability of 75% of me having to wait. And that's a really strong narrative. So if you are fighting upper administration, if you're fighting government officials, emergency managers for extra units. You want a couple extra ambulances on the road. That's a really, really strong story right there. So we've got 5 ambulances right now, and you do these calculations and you say, you know what, sir, you know what, ma'am, if you call 911 between 6 a.m. and 7 a.m., there's a 75% chance you will have to wait for an ambulance above and beyond our normal responses. Um, and that will get a reaction. So, we can play with the numbers, and again, you can um, present these to your upper administrators, to your city council, county commissioners, whoever is the decision maker on that end. If you're on the public side. So, what if we increase the number of ambulances? So we went from 5 to 8. We still have a lambda of 3. Average number of calls is staying the same. We're just increasing the number of ambulances. Our mu at 0.67. Our average runtime is still the same. Average total call time is still the same. All we're doing is increasing the number of ambulances, and that increases my P0, the probability that all of my units will be available during that time. Remember, we started at 0.5%. Well, now we have more than doubled that, and we are at 1.2%. So still a pretty low probability, but we've doubled that probability of all of our ambulance units being available. Again, that's a pretty powerful story using statistics as your friend. Still relatively low probability, but it's been doubled. And with that doubling of that P0, we now see our probability of waiting decreases from 75% to 6%. And that's one of those oh my gosh moments when you are presenting that or trying to get some extra units. You say, hey, here's what's going to happen if we add some ambulances. So you call 911 between 6 a.m. and 7 a.m., your probability of waiting for an ambulance above our normal response drops from 75% to 6%. So pretty powerful story, pretty powerful narrative using these calculations. So we used a time period of 6 a.m. to 7 a.m. for our examples, and these calculations are going to have to be repeated for each hour, taking into account average number of calls and average total call times, and that's going to take a while. That's going to be hard to do by hand. It's going to be tedious. It's just going to be a waste of your time to do by hand for every single hour. And that's why we have computer models. That's why we have computers. That's why we have Excel spreadsheets. We can just plug in some numbers and let the computers do the work for us. So like we said at the beginning, please don't commit these formulas to memory. This isn't something to memorize. Just know the thought process, the mathematical process behind it, and what exactly it is that it's telling you. As always, please let us know if you have any questions, comments, concerns, or cuss words.